So the motivation for this talk, or for the work I want to talk about, is trying to understand these things called Gauss uniformity norms and functions that have not too small values for the Gauss uniformity norms. So let me first write down what the Gauss uniformity norm is, just say on Z mod n, and then talk a little bit about why it's important. So suppose that f is a function from Z mod n to the complex numbers. Then I'll just give you the definition to begin with. The kth, so the order k Gauss uniformity norm, is the following expression, so it's quite complicated. Where this. Right. So, what's going on? So first, really, I want to focus on this part. This is some kind of multiplicative analog of a differencing operator. You have a function on Z mod n, you rotate it by this fixed element u, and then multiply by its conjugate. So I'm multiplying by a conjugate rather than an inverse, but this is some kind of multiplicative differencing operator. And so to define the norm, I average over all base points n, and then over all k tuples of possible differencing parameters. And for all of those, I form this expression, which is the composition of these k differencing operators applied to f. And then I average over all the parameters. There's the averaging. And then I have to take a 2 to the kth root to make this homogeneous of order 1. And then it's a result, which I won't show you, that this is actually a semi-norm. This is it's a norm, I think, if k is at least 1. Is that right? Somebody else. 2. Okay. Norm k is at least 2. Okay, so right now this is just a mysterious formula. The reason this is important is that it appears as a tool, at least the first reason it's important, is that it appears as a tool in Gauss' proof of Semirates' theorem, which, as many of you know, is the proof that gives much the best bounds. So what I want to talk about is just briefly remind you why it appears in that proof and what role it plays. And having said that, it'll be clear what it is we want to know about this norm, and in particular what functions take certain values for this norm. And then I can explain what is the problem that actually motivates the real subject of the talk. So the reason this comes up in Gauss' proof of Semirates' theorem is that if you have a subset A, well, actually, let me say something else first. So I'm going to make another definition, and then I'll talk about Semirates' theorem. So related to this is another quantity which now depends on k functions from Z mod n to the complex numbers. I'm going to write this lambda. And what this is an average over all arithmetic progressions in Z mod n. So I'll be averaging over the base points and the common differences of the product of the values of these functions at the points of that progression. Okay, so this is just some other definition at this point. This is a multilinear form in these k functions. So if you fix all but one of them, then it's linear in that one. And the reason this quantity comes up in studying Semirates' theorem is that if you have a subset of Z mod n, and you apply the form lambda to k copies of the indicator function of that subset, then what happens is that this product expression is either 0 or 1, and it's 1 if and only if all of these points are in the set. So this is just counting what fraction of all the k arithmetic progressions in the world lie inside the set. So this is the proportion of KAPs lying in A. And so Gauss' proof, and really implicitly all of the proofs of Semirates' theorem, actually show you that if A has a fixed positive density delta, then this quantity can be bounded below by some positive C of delta, since, for very large n, a vanishingly small fraction of all the KAPs in the world are degenerate. They have, so almost all of them have k distinct terms. Once you know that this has a positive lower bound, you know that for large n you've found some k arithmetic progressions. Okay. So that's what this has to do with Semirates' theorem. It's natural to try and estimate this rather than look for particular progressions because this averaged quantity behaves more smoothly. And then the norms come up as a means of controlling the values of this multilinear form. So that control is by virtue of, I guess I can go here, something called the Gauss-Cauchy-Schwarz inequality. So this says that if you have your k functions from z mod n to the complex numbers, then you can pick one of them. So you can pick some I between 1 and k, and then you can control the value of this multilinear form, the absolute value, using the u, I think it's k minus 1 norm of your chosen function and the L infinity norms of the others. So it's obvious, it's very easy to see you can control this just by the product of all the L infinity norms, but actually you can choose one of them and replace it with this uniformity norm. And that's actually a lot better because this is often much smaller. Okay? So that's the Gauss-Cauchy-Schwarz inequality. This is proved by an iterated appeal, I think, to the Cauchy-Schwarz inequality k times, or k minus 1 times, I guess. So if we're counting applications of Cauchy-Schwarz, there's k minus 1 right there. And this means that for many sets, you can say very quickly that they contain a lot of k arithmetic progressions, because if you have a set whose indicator function is close to its expectation in the uk minus 1 norm, so I'm going to write delta for just the density of the set A, so cardinality of A over n, then when you look at this multilinear form applied to the indicator function of A, I can swap out the first indicator function for the constant delta and incur a small error because this difference is small and all of the functions are uniformly bounded by 1. So this is approximately lambda with a delta and an indicator function. And then I can do the same for the second entry and so on. And after doing this k times, I get that the density I really care about is roughly lambda of several copies of the constant function delta, which is delta to the k. So provided this is less than delta to the k over k, I get my positive proportion of k arithmetic progressions. So that tells you that for those sets which satisfy this inequality, you already know there are many k arithmetic progressions contained inside them. And for example, you can check very easily, you can check directly, but you can also check using these norms, that a random set is very, very likely to satisfy these estimates. So a random set has a very highly, in the randomness, there's very high concentration in the number of k arithmetic progressions, and it's roughly this proportion. So in Gauss' proof of Semirades theorem, the first step is to introduce these norms and give this very simple deduction, and then the hard work is in treating the opposite case. So if you've heard about the division, somehow philosophically, between the structured and random cases in proofs of Semirades theorem, this tells you what the random case means. It means sets that satisfy this inequality. And then the structured case, which is the bulk of the work, is to try to understand what it tells you about A if this inequality is violated. Okay. So, just write something. The main work for proving Semirades is to understand the structure, whatever it means, of those. Well, I really care about those sets, but in general it makes sense to study the larger class of functions. Those functions f such that this Gauss uniformity norm is not too small. So it's bigger than some threshold that you chose, say eta. Also, so I've said it makes sense to enlarge the class of objects you look at to functions, but I don't want to allow functions for which this is large because of having some very tall, narrow spike, so I'm going to look at functions to the unit disk. Okay, so this is often called the inverse problem for the Gauss norms. it asks for some structural description of the functions that satisfy this. And if you get a good enough description, then the idea is that having handled the case of random sets, you can use that structure to prove that the sets in the remaining case must also contain some positive proportion of arithmetic progressions for some different reason, for some structured reason. And that's how Gauer's proof and more recent variants of it go, of Semiramis' theorem. So implicitly in Gauer's work, there is an answer to this inverse problem. So Gauer's gives one answer, and then more recently there's been a more technically sophisticated and precise answer given in terms of these objects called nil sequences by Greentown, Ziegler, and Segedi. And I won't go too much into exactly what they showed. But we actually do know fairly well what the right answer to this question is in this one-dimensional setting. It's technically quite complicated, but we do have a very good description. So what I want to talk about, I haven't forgotten anything. Right, what I want to talk about is what happens if you try and mimic this approach in the case of the higher dimensional Semiramis theorem. So let me formulate this the way I want. So now you fix some positive delta, and you also fix a finite subset of ZD. Then, if n is large enough, depending on delta and also on the size of this finite set, and you have a subset now of Z mod n to the D, whose density is at least delta, then A must contain some translated and dilated copy of this F, where I read F mod n. And also this has to be non-degenerate, so that you must be able to find such a translate and dilate so that no two distinct points of F are identified. So the one-dimensional Semiramis theorem is just this theorem. Sorry, this also depends on D. Okay. So the one-dimensional Semiramis theorem is just this theorem where D equals 1 and F is a fixed k arithmetic progression, say from 0 up to k minus 1, and then this becomes a general arithmetic progression. So this has various proofs, like the original Semiramis theorem, using ergodic theory, using hypergraph theory, but there's no analog of the Gauer's approach that's been completed in this setting, except for one special case due to Skradov, which I should mention but won't tell you too much about.
Does Skradov only depend on the size of F and not actually configuration?
There is a bound that depends on the size of F, yes. And there's actually, with a little bit of playing, there's sort of, for any fixed size, there are universal Fs. So you get it from that. So what I want to do is try and tell you what happens if you try to mimic Gauer's approach in this setting. So again, it's easy to write down the relevant multilinear form. So suppose F has size k. I should do better than that. Suppose F is the set V1 up to Vk. Then the relevant multilinear form is now an average over all translates and dilates of F. Of the product of the values of these functions at the corresponding points. Of that translate and dilate of F. So far so good. This is the right quantity to study. Now you want an analog of the Gauer's Cauchy-Schwarz inequality, and you get that too. Says that this value lambda is bounded by the product over the j's not equal to your chosen I of the L infinity norm times something like a uniformity norm, but now it's not the most simple analog in higher dimensions of the uniformity norm we had before. Now it's something that has to remember the directions of these vectors v1 up through vk. And actually what happens is that the uniformity norm you have to apply to the ith function depends on the differences between vi and the other vectors. So vi minus vk, not vi minus va. So this is some new Gauer's norm, some new uniformity norm that depends on the choice of certain directions. Now let me tell you what it is. So for some choice of direction, say u1 up to uk, this is again going to be an average over base points in the whole group, and then over some differencing parameters. But now these will only run over z mod n. And that's because inside the expression that we average, we're only allowed to apply the differences in the directions given by the ui's. So along multiples of those ui's. K, Fn, and then again there's a 2 to the minus k outside. And I guess there's an n to the minus d minus k here. Okay, so this is the higher dimensional Gauss uniformity. This is the directional Gauss uniformity norm. And this is where this approach gets stuck, because we don't have a good inverse theory for these norms.
Even in the one-dimensional case, this seems to be more general than what you talked about.
Yeah, but not very much. In one dimension, it's not very much more general. Because, well, okay, in one dimension, there are some arithmetic issues, but in one dimension, if, for example, you're in Z mod a large prime, then all of these will just run over the whole group. So it's the same. It's really, the issue is really that you might have these one-dimensional directions in a higher dimensional group, and you're constrained to difference along those. Okay, so again, there are some other special cases where we do have a good inverse theorem for this, and I sort of morally feel like I should tell you more about them, but I'm going to hide that. Because it is true that in general, we do not have an adequate inverse theory for these norms to use in a proof of Semiramis theorem, or for anything else, really. So, what I want to talk about today is some work related to this question, but only to a very basic toy instance of this question. So I certainly can't give you any kind of inverse theory for these norms in general. What I want to ask instead is, what does it mean if a function actually takes its extremal value for these norms?
So there is a conjecture for an inverse?
Sort of. I'll tell you what it is in a little while. Sort of. A conjecture that I'm not sure I believe, so it's not my conjecture for sure. But anyway, we'll come back to that. Okay, so the toy problem, or maybe better to say the extremal problem, is to describe those functions f, and again I'm going to let them go anywhere into the unit disk, but I want to rule out functions with spikes. That's somehow not the phenomenon of interest, for which this quantity is actually maximized, rather than just somewhat large. So let's quickly think what that means. If you look at this, is an average of values that are all given by products of values of f. Inside here, every time I apply a differencing operator, I take two different values of my function and multiply them. So this is actually a product of 2 to the k values of f in different places. The only way, the best thing this could do is if these all line up somewhere on the unit circle, because this is a norm, it had better be at the point 1. So the maximum possible value is 1. And this happens only if this expression inside the average is actually identically equal to 1. For all n h1 through hk. So the problem I want to talk about is describing those functions f that satisfy this equation. So this is now an algebraic problem. Hopefully, it's simpler than the full inverse problem. So before I go into what we can say about this, let me at least give a little more motivation for studying this very basic special case of the full problem. Firstly, if you're going to solve this, you'd better be able to say something about this, clearly. If you can't solve this, put that another way, if you can't solve this, this is going to be impossible.
Well, you want a different type of answer. You just want correlation with something.
Yeah, but even that would be some information here. I mean, you must learn something about these functions.
So that's not necessarily true. You could hope to show that if you've got the Gauss norm is at least delta, then it's something to do with one of these 100%.
Yeah, okay. But that's actually my next point. That's my next point. So, okay. Very good. If you choose, as I do, to see that as changing the subject, contrary to what Ben chooses, then the next reason to care about this problem is that what happens in one dimension, at least according to Gauer's approach, is that if you have a function on Z mod n whose Gauss norm is somewhat large, his conclusion is that you can find inside Z mod n many long arcs with arithmetic progressions inside them, length something, I think it's n to some epsilon, where epsilon depends on the other parameters, such that on these arcs, your function correlates with an exact solution. And I'll tell you what the exact solutions are in a little while. So in the one-dimensional setting, you find that one version of the general inverse theorem, the original version due to Gowers, is that a function whose uniformity norm is somewhat large has correlations on many large arithmetic pieces of the group with exact solutions. You'd like that to be true in higher dimensions as well, perhaps, but once you have this, you still need to know what the exact solutions are to use that information in proving Semradi's theorem. So we'd better solve this problem as well, if we want to use this in attacking the multidimensional Semradi theorem. The third reason for studying this question is it turns out there's actually quite a lot of very, very varied solutions here, and they're quite pretty in their own right. So hopefully I'll be able to show you that, at least, by the end of the talk. Okay. So that's the algebraic question I want to talk about. I'm going to generalize it a little bit.
That f is from Zn to the d.
Yes. Yes, except, thank you for saying that. So, given that this takes values in the unit disk, in order for this to hold everywhere, it better actually take values on the unit circle. If it goes inside anywhere, then this product...
Just the domain, there's typo. There's a d missing from power of Zn.
F takes d very...
Oh, you're right. I beg your pardon. Yes, yes. I misunderstood you. Yes, that's right. Yes, Z into the D. Okay, but it did remind me of something I need to say, which is that for this to equal 1, F must actually take values on the unit circle, because if it goes inside anywhere, this product can't go back out. So F actually goes from Z mod n to the D to the unit circle. Okay, so I want to generalize the setting just a little bit. And again, I'll tell you why in a moment. I want to work on an arbitrary compact abelian group. So you can think of a finite abelian group like Z mod n to the D, or you can think of a d-dimensional torus, or an infinite dimensional torus, as you like. And I'm going to imagine that I have a collection of closed subgroups, U1 up to UK. And now I want to describe those measurable functions f from z to the circle group, which for me is the real numbers mod the integers, such that the analog of this equation holds. What I'm going to do now is write this equation additively. And that's why I've switched to R mod z, because it'll be easier to write things additively from now on. So such that whenever you pick some elements U1 of the first group and U2 of the second group, and then apply what is now an additive differencing operator, so this is f of z translated minus f of z. Whenever you apply these additive differencing operators at these chosen k elements of the k groups, you kill the function. Does that make sense? So this is what I'm calling a partial difference equation. It's a very naive, discrete analog of an order k linear partial differential equation with constant coefficients. So the simplest kind of higher order PDE you can think of, this is some difference equation analog.
Should we change 1 to 0 then?
Yes, I should. Thank you very much. Yes. Yes. So I'm writing things additively, so this is now 0. So the problem is to describe the measurable functions that do this. Don't worry too much about the measurability requirement. As you know, that's something extremely weak. It is important for the theory that follows, but it's not a serious constraint in what I'm going to tell you about. The reasons for making this generalization, firstly, well, there are three reasons. Firstly, it somehow clarifies a lot of what's going on, because a lot of what I want to say is not special to Z mod n to the D, and it makes sense to work in a more general context. Secondly, it also allows me to cover other finite abelian groups, such as vector spaces over a finite field, where there are also versions of the multidimensional Semradi theorem that you would want to attack. So it covers all of those at once. That second reason is enough to motivate you to study a general finite abelian group. But the third thing is that for some of the theorems that we can prove here now, various parameters that come out do not depend on the group, but the only way I know how to prove that is by some limiting compactness argument. And when you run that argument in the limiting problem, you get a group that's not finite. You get a torus or something. So you really want some compactness in the space of problems, which I won't go into in too much detail, to run those arguments. Okay. So that's the setting I'm going to work in now, and this is the problem I really wanted to talk about. Okay. So now let me very quickly show you some example solutions to some example problems. Firstly, the simplest case, somehow algebraically, is when all of the ui's are equal to the whole of z. And that corresponds to what we said in the one-dimensional Semeradi theorem, where you have these directions in z mod n, and you're assuming that they cover the whole of z mod n. So now you have a function from z to the unit circle, and you're asking that whenever you form any differencing operators of it k times, you kill the function. And for any sensible definition, this is equivalent to f is a polynomial of degree at most k minus 1. So in the case of, say, z being z mod n to the d, or also you could ask this question on zd. I didn't say this very well. Let me write that in a slightly more precise way. Yeah, so in case you're on z mod n to the d or z to the d, this is saying that if you difference your function any way you like, k times, you kill it. That's a characterization of polynomiality. Because I'm going into t, I should say that f equals, say, p mod 1, where p is a polynomial. Degree at most k minus 1. Okay, and if you write these multiplicatively, you get something like e to the 2 pi I times a polynomial. And this is what's often called a phase polynomial. And these are the basic objects that appear as the exact solutions to this problem in Gauss' approach. So these are the things that you get correlation with on those long subprogressions in Z mod n. Okay, so that's what happens when the UIs are the whole group. Exactly what polynomial means does depend on Z. So if you're working in Z mod n, then you can use your naive definition as a sum of monomials. If you're working on the circle group, the continuous circle group, then actually there are no polynomials of degree higher than 1. So there are affine functions and then it stops. So it does depend what group you're working on, but this is the answer for any sensible interpretation of polynomial. Okay, so that's one example. Let me show you another extremely different example, but also very simple. In general, you could just let f be a sum of functions, f1 up to fk, where fi is ui invariant. So what that means is that inside the big group Z, fi is constant on all the cosets of the subgroup ui. So then the ith differencing operator here kills the summand fi, so the composition kills all of them. It's another very simple example. And having noticed that, you can also generalize these two classes of example by choosing some subcollection of the ui's and using a function which behaves as a suitable polynomial on every coset generated by that subcollection. So let me just write this. So you're looking at all possible subcollections of the groups U1 up to UK. Say they're indexed by this subset E. Then having chosen a subset E, you form the sum of those subgroups of Z. So maybe Z is a 100-dimensional torus and you chose 7 4-dimensional subtoruses and you add them together, that gives you a subgroup. And then you ask that Fe be a polynomial of degree at most the cardinality of E minus 1 on every coset of that subgroup. And then this will be annihilated by the product of the differencing operators just coming from that subgroup. So each of these is killed off by this smaller differencing operator for this reason. And so the whole thing is killed. Make sense? Okay, so if you're like me, you play for a while and you come up with these examples, and then you play for much longer and you don't see anything else, and you begin to think that that's everything. But it's not. So here is example 4. So let Z be the 3 torus, and let f of the 3 coordinates be the following function, where I'm going to write it and then tell you what it means. So this is a fractional part notation. What this means is I take an element of t, r mod z, and I look at its representative in the half interval from 0 to 1. So this is in 0, 1. So this sum is a sum of two real numbers. It's between 0 and 2. So the integer part is either equal to 0, in which case the whole expression is 0, or equal to 1, in which case I take the value t3. So you can draw a picture of this function. Here is the 3 torus. Maybe I'll use a different color. What this function is doing, it's cutting the 3 torus into two pieces, depending on the t1 and t2 coordinates. So it cuts it into the piece on this side of that diagonal plane and that side of the diagonal plane. On this side it's 0, and on that side it agrees with the third coordinate. So it still has some polynomial flavor, but it has this cut in the middle, which is very much not a polynomial flavor. Okay, so I'm here to tell you that this is killed where U1 is the subgroup given by the first coordinate, U2 is the subgroup given by the elements t, comma minus t, comma 0, and U3 is the subgroup 0, t, minus t, and U4 is the subgroup given by the last coordinate. So you can go in and check that if you feel like it. If you difference by any elements of these groups, you get 0. Okay, so that's a fun fact. I should also mention, this didn't just come out of the hat. I didn't just wake up one day and realize that this was a solution. This function actually means something in group cohomology, and the fact that it satisfies this equation is a consequence of a very important equation in group cohomology that this function satisfies, which I'm not going to go into in too much detail.
So also in dimension 1 there are these fractional polynomial, right?
Yeah, so it's a funny thing. In dimension 1, in classical theory, these fractional polynomials come up in the solution of the full inverse problem, but not the exact problem.
Not in the exact problem?
No. But here, this is really a solution to the exact problem, and it really needs this integer part. I mean, I haven't proved that it really needs it, but it does. I'll tell you what I mean by that in a little while. Okay, so there are these more exotic solutions, and actually, once you know that you get these solutions coming from group cohomology, you can produce more and more complicated examples. You can actually produce huge families of very funny-looking examples, but they do all involve these integer and fractional parts somehow.
So which group cohomology? I mean,
Calvin Moore's measurable group cohomology for locally compact groups and Polish modules. It's, you know, there's 100 group cohomologies out there. There's a right one. Gives you this. Ask me after and I can tell you a lot more about it. But for now, there is one. It works for groups like the circle into the circle, and this is what you get. Okay. So there are these more exotic solutions. And at this point, my feeling is that you can't hope for a really complete answer to this question the way we have in one dimension. You can't hope for an answer that just says, take a sum of monomials. But you can still say quite a lot about the solutions. So what I want to do now is tell you some things that we can prove about solutions to this problem. So some general results. So first, let me set up some notation. I'm going to write f of z to t for the group of all functions from z, all measurable functions from z to t. And as usual, I will allow myself to identify them up to equality almost everywhere. That doesn't matter at all for finite groups. So having done that, this carries a natural topology. You can see it as for an LP topology or so, or the topology of convergence in probability. And then provided z is reasonably nice, so provided z is not enormous in some set theoretic sense, this is a Polish group. That means it has a complete separable metric generating its topology. So it's something like a separable Banach space, except it's not a Banach space because these are not functions into a field, they're functions into the circle. But somehow, from a soft general topology point of view, it's something like a Banach space. Okay? It is a group, and moreover, z acts on it just by translating the argument of the function. So it's actually a Polish z module. And inside this, I want to pull out a collection of submodules. I'm going to write them ME. These are the functions which are annihilated by the differencing operator that just uses the subgroups indexed by E. So let me write it instead as give the subset a name, set I1 up to IL. These are the functions that are annihilated by the differencing operator I get if I only use the subgroups ui1 up to uil. So these are all contained in this big group F. You can easily show they're closed for the topology of convergence in probability. And also, if you rotate a solution to this equation, then it's still a solution. So these are closed submodules. Okay. Also, if you enlarge the subgroup, sorry, the subset, that means you're applying more differencing operators here. So any solution to this equation also satisfies this equation. So as E gets larger, this module also gets larger. Okay, so that much is just notation. So now having written that, let me very quickly tell you what is the most naive thing to do if you want to understand a solution to the full partial difference equation. So an element of M subscript the whole set 1 up to K. So suppose F is in here, we don't know what it is. When you stare at this for a while, there's really only one thing to do, which is to pick one of the subgroups, say UK, apply a differencing operator, and now look at what you have. This, for each little u in UK, is an element of a smaller module, because now this is killed off by the differencing operators that don't use UK. I've already used it, so I don't have to use it again. So this goes into M subscript K minus 1. So what I've really obtained here is a map from UK to the module mk minus 1. Okay, so you have this unknown function that satisfies the order k equation. From it, you can obtain a map from UK to functions that satisfy the order k minus 1 equation. In order for this to be useful, what you would like is to be able to say something about what maps you get out here a priori, before you know the structure of F or the full module. So an arbitrary map is an arbitrary map, but this is not an arbitrary map. This map satisfies one very important relation. So let me call this G sub u. It satisfies the one co-cycle equation. So that means G sub u of z plus G sub v of z minus u is equal to G sub u plus v of z. And that's because if you simply write this out as differences of f, two of the terms cancel and leave you with the right-hand side. So it's very simple. So this G has given you a map from UK into this smaller module, which we're assuming we already understand as part of some inductive hypothesis, which satisfies this equation. So what you would like, ideally, is to be able to say what all the maps are satisfying this equation into mk minus 1 before you know anything about mk. And then you would have the kind of information that would give you another cycle of the induction. So the problem of doing this is precisely a problem in group cohomology. That's what group cohomology studies, or at least degree 1 group cohomology, studies maps from a group like UK into this module that satisfy this equation. So this is the one co-cycle equation. So to use this, you want to study, I'm just going to write down its name in group cohomology. If you haven't seen this before, don't worry about it. Some algebraic object which describes, up to some natural equivalence, all the maps from UK into this module that satisfy this equation. This is called H1. This is the first group in group cohomology. So the nice thing is that if you know enough about group cohomology, you can compute this, provided you know abstractly what the module mk minus 1 is. I'm telling you this because it leads to a very important shift in our point of view. Instead of studying individual solutions, I'm first going to try and understand the structure of the whole module as an abstract group. Having done that, I can work out what this is, and hopefully get the structure of mk from this. So, change of emphasis. To studying the whole module. Okay, so let me tell you the first main theorem about these modules, and then I'll just mention that you can actually get quite a lot about individual solutions from this as well. So I'll write the theorem in a moment. What I want to bring up now is that, as mentioned here, if you have a solution to a simpler equation, it's also a solution to the more complicated equation. So a natural first question to ask about the module of all the solutions is to ask for a description of them modulo the simpler ones. So let's say that elements of the sum of all the simpler problems are degenerate solutions. So these are the functions that satisfy the full equation because they can be written as a sum of things that satisfy strictly simpler equations. So the first thing I want to do is understand the structure of M sub k modulo this. Okay, so here is the theorem, and this is the start of a larger picture that I probably won't give you in full. Subject to some condition, it's a very simple condition that I will come back to in a moment, this quotient is discrete. And moreover, I'll write this and then talk about it, its separation is bounded only in terms of k. Okay, so let me just go over this. Firstly, I'm going to assume this somehow non-degeneracy condition on the problem, that the ui's together span the whole of z. If that's not true, then you can just choose a separate solution on every coset of this sum and produce a solution on the whole of z. So the general picture is just this picture on each coset of the sum of the ui's separately. So you can easily reduce to this case. Having done so, what you find is that, this is if k is at least 2. Once k is at least 2, all the solutions take the form of some element of a discrete list of well-separated solutions plus degenerate ones. So there's a discrete, and actually if z is a reasonable group, this is what has to be countable. There's a countable list of well-separated solutions to this problem, and everybody is one of those plus a degenerate solution. Moreover,
Separation is, you said what metric?
yeah, so choose your favorite metric. Convergence, anything that gives you convergence in probability, this will be true. I mean, the constant will be different, but just choose something that gives you convergence in probability. So choose L1. This is not it's not the whole Banach space. They're not real valued. It's just to the circle. There's no functions with spikes. Okay. Yeah, so choose your favorite metric giving convergence in probability. Then you can choose this countable list so that even if you modify the entries by degenerate solutions, whatever you do, modulo degenerate solutions, they all have to stay far apart, and how far apart they are doesn't depend on the groups. Z or U1 or U2, it only depends on how many of them there are. So this is non-trivial even for finite groups. Like the whole thing is non-trivial even for finite groups, but this is the surprising part, and that's where I needed some compactness argument. Having said this, I also want to tell you without writing anything that the proof of this implicitly gives you an algorithm for calculating this exponent. It's a very, very long, this quotient. It's a very long, impractical algorithm, but the proof of this is that you have, if it's in principle, some procedure for computing what this is, and then you can show that it carries qualitative properties along with it. So you feed in ingredients that satisfy some version of these hypotheses, and what you get out has to satisfy them too. This is a very standard thing in homological algebra, that you write down some enormously complicated calculational procedure that you would never actually run, but you show that it preserves the qualitative features you care about. So that's how you get this. And then this is actually just a top case of a more complicated conjecture that I guess I won't show you. Let me just finish by mentioning a couple of other things that you can get from the same algorithm. So firstly, once you know this discreteness, you can solve not only the 100% extremal case of the Gauss inverse problem, but also the 99% case. So theorem B. So for every epsilon and k, there is some eta such that if you have a function g from z mod n to the d to the unit disk, and this Gauss uniformity norm is bigger than 1 minus eta, so it's very, very close to maximal, then it's because g is actually within epsilon, say in the L1 norm, of an exact solution. So there's a stability result. And once you cook this correctly, you see this follows fairly easily from this discreteness.
So wait,
Not trivial, but...
give the characterization of all the...
So this is just a qualitative assertion about these modules. But the proof of this also gives you an algorithm that in concrete cases you can use to compute exactly what the quotient is and compute a list of representatives.
So can you say succinctly what the exact the exact solutions are?
No. No, I can't, and I'm sure that it's not possible. I mean, the world of them is enormous. It's a very, very long algorithm with many steps that produces eventually some funny list. But it's not as simple as in one dimension. I don't think there's a succinct way of writing it. Let me tell you one final thing. I've gone over time, but this will be very quick. Another qualitative feature that you can carry forward when you run this algorithm is that you can choose for this list of basic representatives. So in theorem A, choose list of representatives which are generalized polynomials. So let me just draw you a picture to say what that means. If you're imagined on a torus, so imagine you're on a torus, a generalized polynomial is a function that cuts the torus into finitely many polyhedral pieces. And on each of those pieces, it's given by some simple polynomial expression. So this is what happened in that last example I showed you. It cut the 3 torus into 2 pieces and gave you something linear. You can find examples that cut them into more pieces and give you higher order functions on the pieces. That feature is irremovable. But you can always find functions that have this algebraic form. They're not arbitrary measurable functions. And then there's some very messy quantitative version of this.
It's polyhedral.
Yes.
So it's not like lower degree polyhedral.
No. Really polyhedral. Yes.
What is this picture? This is a torus?
This is a 2 torus. Yeah.
There's a smile in the middle.
So smile. Yeah. Okay. Okay. So I'm sorry I went over time, but that's part of the story. Thank you very much.
So you mentioned there's some conjectures about inverse Gauss.
Yeah. So the conjecture is actually what Ben referred to. That the full inverse story is that if a function has not too small uniformity norm, then you can find these big pieces of z mod n to the d on which it correlates with an exact solution. So it correlates with somebody in here. I'm very agnostic about whether that's true, or maybe I'm a little bit skeptical, but that I think is the conjecture, unless you want to add to that.
I was going to say, well, suppose that is true, and suppose within what you've just told us you make some other sort of reasonable conjectures. Is there a program for generalizing what Shkredov did to arbitrary dimensions?
Yes.
What
I'd rather
Shkredov
not
did?
try and describe it directly,
What
but yes,
Shkredov
there
did?
is.
What did he do?
So Shkredov has given a new proof of the case of the two-dimensional sum-radius theorem where you look for these upright isosceles corners. And for that, he gets some inverse theorem for a particular Gauss norm, and he can extract enough information from it to get this improved bound. And then I think he can also do the case of a configuration where you have an L. So you have a point and a base point and then 2 points above it, something like this. But for example, a square, we don't have improved bounds for the multidimensional sum-radius theorem where you're looking for a square. So that would be the next case to try. If you could prove this full version of the inverse theorem using these functions, then that would, yes, give you a program for attacking that problem. Its success, of course, depends on the bounds, and I haven't said anything about bounds. The bounds here already are pretty terrible.
Even ignoring the bounds, I mean, you said it seems to be very difficult to classify these 100% functions in these generalized Gauss norms.
Right.
But you can sort of do that somehow enough, or at least conjecture you can do it enough to be useful in this context?
Yeah, because I think this kind of qualitative feature, if you can control the complexity of this representation, you can't write down a list of all the polyhedra you might need, or all the pieces you might need, but if you know this kind of regularity with good enough bounds, that should be enough. Yeah. Yeah.
So just to be clear, if you did know this conjecture, that something with 1% correlate, the 1% solidity result basically, having a structure which correlated like with one of those, then this would imply like good bounds for.
No. This would give you a program to go look for good bounds.
Right.
Right.
So,
Getting those bounds would depend on the quality of the bounds in that inverse theorem, and I have no idea what they would be.
Right.
Yes.
Also, just one remark, it looks that, from my point of view, this question of understanding the extreme function is as exciting, if not even more exciting, than just pushing the bounds for high.
Oh, I'm really glad you think that, because I think that too, but I was very nervous about saying that to a combinatorics audience. But I agree.
But on the other hand, I would like to ask, still, even Gauss norm is not so sacred, so maybe there are other norms, especially in high dimension, even in one dimension, that can play a similar or even better role.
Yes. I don't think you're going to avoid... Well, okay. So let me just say something very briefly about this. I don't think you're going to avoid having to solve some problem like this.
Yeah.
And I'm saying that partly because you can ask a related question which doesn't involve the extremizers of the Gauss norms, where, yeah, you can instead you can just ask for tuples of functions f1 up to fk on, say, z mod n to the unit circle, for which the expression, the product that you care about, is identically equal to 1. And if you have some tuple of functions that satisfy this, then taking level sets of those, you can produce a very anomalous set from the point of view of the multidimensional Semeradi theorem. And describing these tuples is actually a special case. The same methods give you a full description here. Or, no, not a full description. They give you an analogous description here. So I think you can't... I could have given the whole talk about this problem and all the conclusions are qualitatively the same.
So basically you're saying you can use all these things, everything you get from here to...
Yeah, just to study tuples of functions whose sum has some vanishing property. The whole story is analogous.
More questions?